take a deep breath. Let it fill your lungs slowly, gently, and as you release it, feel the weight of the day beginning to lift from your shoulders. Tonight, we're embarking on a journey together, a voyage through the darkest, most mysterious objects in the entire cosmos. But don't worry about following every detail or remembering every fact. Just let the words wash over you like gentle waves on a distant shore, painting pictures in your mind of wonders so strange and beautiful that they exist at the very edge of what we can understand. Before we begin, if you find comfort in these cosmic explorations, if the universe's mysteries help quiet the noise of daily life, consider subscribing to the Science Pillow. With each video, we venture into the unknown together, exploring the wonders of science while helping you unwind and relax. A simple like helps others discover this peaceful corner of the cosmos too. And now, let's drift into the darkness, where black holes await. The nature of black holes. A foundation. Imagine, if you will, a place where gravity has become so intense, so utterly overwhelming, that it warps the very fabric of reality itself. Picture space-time, that invisible mesh that connects every point in the universe, being pulled and stretched and twisted into a funnel so steep that nothing, not even light itself, can climb back out once it has ventured too close. This is a black hole, and it represents one of the most profound consequences of the laws that govern our universe. The story of black holes begins not with a telescope pointed at the sky, but with equations scratched onto paper, with the pure mathematics of gravity taken to its logical extreme. In 1774, long before anyone had conceived of Einstein's relativity, an English clergyman and natural philosopher named John Michell pondered a curious question. He knew that gravity pulled on everything with mass, and he knew, as people believed at the time, that light itself had mass and could be influenced by gravity. So Michel wondered what would happen if you had a star so massive, with gravity so strong, that even light couldn't escape from its surface. He called these hypothetical objects dark stars, and though his understanding of light was incorrect by modern standards, his intuition was remarkably prescient. More than a century later, in 1915, Albert Einstein published his general theory of relativity, fundamentally changing our understanding of gravity. Einstein showed that gravity wasn't just a force pulling objects together, as Newton had described it. Instead, gravity was the curvature of space-time itself. Massive objects, Einstein realized, create wells and valleys in the fabric of the universe, and other objects roll along these curves like marbles on a rubber sheet that's been weighted down in the middle. Within months of Einstein publishing his equations, a German physicist named Karl Schwarzschild, serving in the German Army during the First World War, found an exact solution to Einstein's field equations. Schwarzschild's solution described the space-time geometry around a perfectly spherical, non-rotating mass, and buried within his mathematics was something startling. For any given mass, there existed a critical radius. If all that mass were compressed within this radius, the curvature of space-time would become so extreme that a boundary would form, a point of no return beyond which nothing could escape. We now call this boundary the event horizon, and the radius that defines it bears Schwarzschild's name. At first, physicists thought these Schwarzschild solutions were merely mathematical curiosities, pathological cases that wouldn't occur in the real universe. Surely, they reasoned, nature would find some way to prevent matter from collapsing so completely. But as decades passed and understanding deepened, it became clear that black holes weren't just possible. Under the right conditions, they were inevitable. The event horizon is perhaps the most defining feature of a black hole. Picture it as an invisible sphere surrounding the black hole's center. Outside this sphere, in normal space, things behave more or less as you'd expect, though space-time is curved and gravity is strong. But cross that boundary, step over that invisible line, and the rules change fundamentally. Inside the event horizon, all paths through space-time lead inexorably inward, toward the center. The escape velocity, the speed needed to break free, exceeds the speed of light. And, since nothing in the universe can travel faster than light, nothing that crosses the event horizon can ever return to tell us what lies within. The size of this boundary depends entirely on the black hole's mass. For a black hole with the mass of our Sun, the event horizon would be a sphere about 6 kilometers across, smaller than most cities. For a black hole 1,000,000 times more massive, one of the monsters that lurk in the hearts of galaxies, the event horizon might span millions of kilometers. The more massive the black hole, the larger its event horizon, though the relationship is linear and simple. Double the mass, double the radius. But the event horizon is just a boundary, a surface in space that marks the point of no return. At the very center of a black hole, according to general relativity, lies something even stranger, a singularity. This is a point, or perhaps a ring in the case of rotating black holes, where all the black hole's mass is concentrated, where the curvature of space-time becomes infinite, where our current understanding of physics simply breaks down. The singularity represents a fundamental limit of general relativity, a place where the theory, so successful at describing everything else in the universe, loses its predictive power and admits that something else, some theory of quantum gravity we haven't yet discovered, must take over. What happens at a singularity? We honestly don't know. The mathematics suggests infinite density, infinite curvature, a point where space and time cease to have their usual meanings. But most physicists suspect that before we reach true mathematical infinity, quantum effects, the strange behavior of matter and energy at the smallest scales, become important and change the picture in ways we can't yet calculate. The singularity remains one of the deepest mysteries in physics, hidden from our view behind the event horizon's protective veil. Black holes challenge our intuition in profound ways. They're not objects in the traditional sense. They have no surface you could touch, no material substance you could analyze. A black hole is more like a feature of space-time itself, a permanent scar or wound in the fabric of reality. They are defined not by what they are, but by what they do. They curve space-time so severely that they create regions from which escape is impossible. And yet, despite their simplicity in some ways, black holes are also incredibly rich phenomena. As we'll explore throughout this journey, they come in different sizes, from those barely more massive than stars to titans millions or billions of times heavier than our Sun. They can spin at nearly the speed of light or hardly rotate at all. They can be actively feeding, growing ever larger as they consume matter from their surroundings, or they can sit dormant and invisible in the darkness of space. They can emit powerful jets that stretch across galaxies, or they can quietly evaporate over incomprehensible spans of time through quantum processes we're only beginning to understand. The discovery that black holes actually exist in nature, not just in theoretical papers, came gradually through the second half of the 20th century. Astronomers detected X-rays from binary star systems where something invisible was pulling matter from a visible companion star. They measured stars in the centers of galaxies orbiting around something massive and dark. They recorded flashes of gamma rays that could only be explained by the most violent collapses of massive stars. And in 2015, in one of the great triumphs of modern science, physicists detected gravitational waves, ripples in space-time itself, emanating from the merger of two black holes more than 1 billion light-years away. Today, we know that black holes are common in the universe. There may be 100 million stellar mass black holes in our Milky Way galaxy alone, silent and dark, revealed only when they happen to have a companion star to feed upon. Virtually every large galaxy has a supermassive black hole at its center, and these central engines have shaped the evolution of galaxies throughout cosmic history. Black holes are not merely exotic curiosities. They are fundamental players in the cosmic drama, sculpting the universe we see around us. As you settle deeper into comfort, as your breathing becomes slow and rhythmic, let's begin our journey through the different types of these remarkable objects. We'll start with those born from the deaths of stars and travel all the way to hypothetical black holes that might have formed in the first fraction of a second after the Big Bang itself. We'll explore the physics that makes them possible, the observations that reveal their presence, and the profound questions they raise about the nature of reality. Stellar mass black holes, born from dying stars. Our journey begins with the most common type of black hole, those formed from the violent deaths of massive stars. These stellar mass black holes are scattered throughout every galaxy, remnants of stars that once burned brilliantly but met a fate from which not even light can escape. To understand how stellar mass black holes form, we need to understand the life cycle of massive stars. Stars are in many ways simple objects. They're enormous balls of gas, primarily hydrogen, held together by their own gravity. In their cores, tremendous pressure and temperature force hydrogen atoms to fuse together, creating helium and releasing energy in the process. This energy, the light and heat of nuclear fusion, creates an outward pressure that balances the inward pull of gravity. As long as a star has fuel to burn, it maintains this delicate balance, shining steadily for millions or billions of years. But all stars eventually exhaust their fuel. For stars like our Sun, with relatively modest mass, this ending is gentle by cosmic standards. When the hydrogen in the core runs out, the star expands into a red giant, fuses helium in its core for a while, then gently puffs off its outer layers, leaving behind a dense core called a white dwarf. A white dwarf is held up not by fusion, but by quantum mechanical pressure, the resistance electrons exhibit to being squeezed too closely together. It will cool slowly over trillions of years, eventually becoming a cold, dark ember in space. But for stars much more massive than the Sun, those with more than about 8 times the Sun's mass, the ending is far more dramatic. These massive stars live fast and die young, burning through their fuel in just a few million years rather than billions. And when the fuel runs out, when the core has fused hydrogen to helium, helium to carbon and oxygen, carbon to neon and magnesium, and so on up the periodic table until the core is primarily iron, a crisis occurs. Iron is special. It's the most stable nucleus. Fusing lighter elements into iron releases energy, which is why fusion powers stars. But fusing iron into heavier elements requires energy input. When a massive star's core becomes primarily iron, Fusion can no longer generate the pressure needed to hold the star up against gravity. The core has nothing left to burn, no way to generate the outward push that has supported the star throughout its life. And so, in a catastrophically brief moment, the core collapses. The collapse happens astonishingly fast. Within a fraction of a second, a core the size of the Earth, containing more mass than the Sun, implodes to a sphere perhaps 20 kilometers across. The matter falls inward at speeds approaching a quarter of the speed of light. The density becomes so extreme that electrons are forced to combine with protons, creating neutrons. In some cases, if the star's core had between about 8 and 25 solar masses, this creates a neutron star, an object so dense that a teaspoonful of its matter would weigh as much as a mountain on Earth. But if the collapsing core is more massive, if it contains more than about 2.5 to 3 times the mass of the Sun, not even neutron degeneracy pressure can halt the collapse. There's no known force in nature strong enough to stop it. The core continues collapsing, compressing past the density of a neutron star, past any density we can properly describe with current physics, until it forms an event horizon. A black hole is born. This moment of creation is marked by one of the most violent events in the universe, a core collapse supernova. The outer layers of the star still falling inward when the core reaches its point of no return, bounce off the incredibly dense collapsed core, or are blown outward by neutrinos streaming from the core's catastrophic compression. The star explodes with a brilliance that, for a few weeks, can outshine an entire galaxy. The explosion scatters the star's outer layers across space, enriching the interstellar medium with heavy elements forged in the star's core and in the explosion itself. But the core, now a newborn black hole, remains, invisible at the center of the expanding debris. Stellar mass black holes typically range from about 3 to perhaps 100 times the mass of our Sun, though there's some uncertainty at both the lower and upper ends of this range. The lower limit is set by physics. Below about 2.5 to 3 solar masses, the collapsing core will form a neutron star rather than a black hole. There's likely a small gap in mass between the heaviest possible neutron stars and the lightest possible black holes, though observations are beginning to fill in this gap with objects right at the boundary, challenging our understanding of where one ends and the other begins. The upper limit is more complex and relates to a phenomenon called pair instability. When stars are extremely massive, with cores between roughly 130 and 250 times the mass of the Sun, something strange happens before collapse. The intense pressure and temperature in the core create gamma rays so energetic that they spontaneously transform into electron-positron pairs, particles, and their antimatter counterparts. This suddenly reduces the pressure supporting the core because energy that had been in the form of radiation supporting the star is now locked up in these particle pairs. The core collapses suddenly, heating up enormously, and the entire star is blown apart in what's called a pair instability supernova. No remnant is left behind, no black hole forms. The star is completely destroyed, scattered back into space. This creates what astronomers call the pair instability mass gap, a range of masses where black holes theoretically shouldn't exist. Stellar mass black holes formed from single stars shouldn't be more massive than about 65 or so solar masses, and supermassive black holes are millions of times heavier. The region in between was thought to be empty, but recent gravitational wave observations have detected black holes with masses in this forbidden range, suggesting they might have formed through the merger of smaller black holes rather than from single collapsing stars. The universe, it seems, has found ways to create black holes that our theories hadn't fully anticipated. In our Milky Way galaxy alone, astronomers estimate there may be 10 million to 100 million stellar mass black holes, the accumulated remnants of massive stars that have died over the galaxy's 10 billion year history. Most of these are completely invisible, dark and isolated, wandering through the space between stars without revealing their presence. We can only detect stellar mass black holes when they have something nearby to interact with. The most common way we discover stellar mass black holes is through X-ray binary systems. Sometimes, a massive star that forms a black hole has a companion star, another star gravitationally bound to it in a binary orbit. If the two stars are close enough, material from the companion star can be pulled toward the black hole by its intense gravity. This stolen gas doesn't fall straight into the black hole. Due to the conservation of angular momentum, the same principle that makes water swirl as it goes down a drain, the gas forms a disk spinning around the black hole, spiraling inward over time. This accretion disk, as it's called, becomes incredibly hot due to friction and compression. The gas in the inner regions of the disk, just outside the black hole's event horizon, can reach temperatures of millions of degrees. At these temperatures, the gas glows brilliantly in X-rays. These X-rays, streaming away from the disk, can be detected by space-based telescopes. By studying the X-rays and the motion of the visible companion star, astronomers can determine that the invisible object must be too massive to be a neutron star and must therefore be a black hole. One of the first and most famous such systems is Cygnus X1, discovered in 1972. Located about 6,000 light-years away in the constellation Cygnus, the Swan, this system consists of a blue supergiant star orbiting an invisible companion every 5.5 days. From the orbital motion, astronomers determined that the invisible object has a mass of about 21 times the Sun's mass, far too heavy to be anything other than a black hole. Cygnus X1 was one of the first objects broadly accepted by the astronomical community as a black hole, and it remains an important laboratory for studying these exotic objects. Over the decades since, astronomers have found dozens more X-ray binary systems that almost certainly contain black holes. Each system has its own characteristics, its own quirks and behaviors, but they all share the same basic feature: a massive, invisible object pulling matter from a companion star and revealing its presence through the energetic light emitted by the superheated accretion disk. More recently, a new method of detecting stellar mass black holes has revolutionized the field: gravitational wave astronomy. In September 2015, the LIGO detectors, massive laser interferometers in Louisiana and Washington state, detected ripples in space-time itself. These gravitational waves were created by two black holes, about 29 and 36 times the mass of the Sun, spiraling into each other and merging into a single black hole about 1.3 billion light-years away. The detection was a triumph, confirming a prediction Einstein had made a century earlier and opening an entirely new way of observing the universe. Since that first detection, LIGO and its partners Virgo in Italy and Kagra in Japan have detected hundreds of black hole mergers. These observations have revealed that stellar mass black holes are even more common than astronomers had thought, and that binary black hole systems, two black holes orbiting each other, are abundant enough that several merge somewhere in the universe every hour. The gravitational waves from these mergers carry information about the black hole's masses, their spins, their distance from us, even the angle at which they're oriented. It's like listening to the universe's most profound symphony, one played not in sound waves, but in the vibrations of space-time itself. These mergers also teach us about black hole behavior in extreme conditions. When two black holes spiral together, they emit gravitational waves that carry away energy and angular momentum, causing the orbit to shrink. The black holes circle each other faster and faster, getting closer and closer, until finally they merge in a violent collision that releases more energy in a fraction of a second than all the stars in the observable universe combined. The resulting single black hole rings like a struck bell, its event horizon rippling and settling into a smooth sphere, sending out one final burst of gravitational waves before falling silent. Some of the black holes detected through gravitational waves have challenged our understanding of stellar evolution. Several mergers have involved black holes with masses in the theoretical pair instability gap, those forbidden masses where single stars shouldn't be able to create black holes. The most likely explanation is hierarchical merging. Smaller black holes merge to create intermediate mass black holes, which can then merge with other black holes to create even more massive ones. The universe may be building its most massive stellar origin black holes not through single stellar collapse, but through multiple generations of mergers, each adding mass and spin to create ever more impressive objects. Stellar mass black holes also likely play a role in some of the universe's most energetic events. Gamma-ray bursts, brief flashes of the most energetic light in the cosmos, sometimes lasting only seconds but outshining everything else in the sky during their peak, are thought to be produced when massive stars collapse to form black holes. The rotating black hole, surrounded by the infalling debris of the star, can launch powerful jets along its rotation axis. These jets, traveling at nearly the speed of light, blast through the star's outer layers and out into space. If one of these jets happens to be pointed at Earth, we see a gamma-ray burst, a beacon so bright that it can be detected from billions of light-years away. As you relax into the darkness behind your eyelids, picture these stellar mass black holes scattered throughout the galaxy like invisible anchors in the cosmic sea. Most are silent and dark, but some actively feed, pulling in gas and glowing with X-rays. Some are alone, while others orbit companion stars or even other black holes. They're the remnants of stars that once blazed in the night sky now, transformed into objects so strange and extreme that they warp the very fabric of reality around them. They're both endings and beginnings, destroying the stars that created them while shaping the evolution of galaxies, and perhaps seeding the formation of even larger black holes. Supermassive black holes, galactic anchors. Now let's journey to the hearts of galaxies, where black holes have grown to truly monstrous proportions. These supermassive black holes are millions or even billions of times more massive than our Sun, and they sit at the centers of nearly every large galaxy in the universe, acting as cosmic anchors around which hundreds of billions of stars orbit. Our own Milky Way galaxy harbors such a beast. At the very center of our galaxy, about 26,000 light-years from Earth, resides a supermassive black hole called Sagittarius A Das, named for its location in the constellation Sagittarius. This black hole contains about 4 million times the mass of our Sun, all compressed within an event horizon roughly the size of Mercury's orbit around the Sun. For decades, astronomers tracked stars in the galactic center orbiting around this invisible point, their motions revealing the presence of an enormous mass concentrated in a tiny volume. In 2022, the Event Horizon Telescope collaboration released an image of Sagittarius A's shadow, the silhouette of the event horizon against the glowing gas surrounding it, providing visual confirmation of what orbiting stars had long suggested. But Sagittarius A is actually quite modest by supermassive black hole standards. Some galaxies harbor black holes 1,000 times more massive. The black hole at the center of the giant elliptical galaxy Messier 87, the first black hole ever imaged by the Event Horizon Telescope in 2019, has a mass of about 6.5 billion times the Sun's mass. Even more impressive examples exist. The galaxy Holmberg 15A contains a black hole estimated at somewhere around 40 billion solar masses or possibly even more. And the galaxy Ton 618 appears to host a black hole that may be 66 billion solar masses, though such extreme estimates come with significant uncertainties. The sheer scale of these objects defies easy comprehension. If you could somehow place one of the most massive, supermassive black holes in our solar system, its event horizon would extend well beyond Neptune's orbit, engulfing the orbits of all the planets. The black hole's tidal forces would be so immense at its event horizon that an object falling in would be stretched and compressed even before crossing the point of no return. And yet, paradoxically, for the very largest supermassive black holes, the tidal forces at the event horizon can actually be relatively gentle. The event horizon is so far from the central singularity that the curvature of space-time, while still extreme, changes gradually enough that a falling object might cross the horizon without being immediately torn apart. How do supermassive black holes form? This remains one of the great open questions in astrophysics. They can't form from single stars. No star is massive enough to leave behind a black hole of millions of solar masses when it dies. Instead, supermassive black holes must grow over time, accumulating mass throughout their existence. One possibility is that they start as stellar mass black holes and grow through accretion, pulling in gas and dust from their surroundings. When a black hole accretes matter, that matter forms a swirling disk around the black hole, heating up through friction and gravitational compression. This accretion disk can be enormously luminous, sometimes outshining the entire galaxy of stars around it. The black hole itself emits no light, but the disk feeding it blazes brilliantly across the electromagnetic spectrum. As the matter spirals inward and eventually crosses the event horizon, the black hole's mass increases. But there's a problem with the accretion-only model. When a black hole accretes matter very rapidly, the accretion disk becomes so luminous that the outward pressure of radiation can actually prevent more matter from falling in. This sets a limit, called the Eddington limit, on how fast a black hole can grow through accretion. If you start with a stellar mass black hole of, say, 30 solar masses, and let it grow at the maximum rate allowed by the Eddington limit, it would take longer than the current age of the universe to reach 1 billion solar masses. Yet, we observe supermassive black holes with billions of solar masses in galaxies we see as they were when the universe was less than 1 billion years old. Somehow, these black holes grew incredibly massive in a remarkably short time. This suggests that either they found ways to exceed the Eddington limit, perhaps through unusually rapid infall of matter that didn't have time to form a bright accretion disk, or they started out more massive than stellar mass black holes. This has led to theories about seed black holes. Perhaps, in the early universe, there were mechanisms for forming intermediate mass black holes, objects of thousands or tens of thousands of solar masses, directly without going through the stellar collapse pathway. These might have formed from the direct collapse of massive clouds of primordial gas, or from supermassive stars that existed only in the early universe when gas had different properties than it does today. These seed black holes would have a head start on growth, making it easier to reach supermassive proportions within the available time. Another growth mechanism is mergers. When two galaxies collide and merge, a common occurrence in the universe's history. Their central black holes eventually sink to the center of the merged galaxy and spiral together. The merger of two supermassive black holes releases enormous amounts of energy in gravitational waves. These mergers have been predicted theoretically, but are challenging to detect because the gravitational wave frequencies they produce are too low for current detectors like LIGO. Future space-based gravitational wave observatories, like the planned LISA mission, should be able to detect supermassive black hole mergers and provide crucial insights into how these objects grow. Supermassive black holes don't just sit passively at the centers of galaxies. They actively shape galactic evolution through a complex interplay of feeding and feedback. When gas flows toward a galaxy center, perhaps funneled inward during a merger with another galaxy, it can feed the central black hole. The black hole's accretion disk flares to life, becoming what astronomers call an active galactic nucleus, or AGN. The most luminous AGN, visible across vast cosmic distances, are called quasars. Quasars were among the most puzzling objects when first discovered in the 1960s. They appeared as point-like sources, like stars, but their spectra showed they were incredibly distant, billions of light-years away. To be visible at such distances, they had to be extraordinarily luminous, sometimes hundreds of times brighter than an entire galaxy of hundreds of billions of stars. Yet, all that light came from a region smaller than our solar system. The only explanation that made sense was a supermassive black hole accreting matter at tremendous rates. The energy released by matter falling into a supermassive black hole is staggering. As gas spirals inward through the accretion disk, gravitational potential energy is converted to heat and radiation with remarkable efficiency. For a non-rotating black hole, roughly 10% of the infalling matter's mass energy can be converted to radiation. For a rapidly rotating black hole, this efficiency can exceed 40%. Compare this to nuclear fusion, the process that powers stars, which converts about 0.7% of mass to energy. Black holes are the most efficient engines in the universe for converting mass to energy. But this energy doesn't just shine harmlessly into space. It can have dramatic effects on the surrounding galaxy. The intense radiation from a luminous accretion disk can heat gas throughout the galaxy, preventing it from cooling and condensing to form new stars. Powerful jets, narrow beams of particles accelerated to near light speed, can blast outward from the black hole's vicinity, punching through the galaxy and heating gas hundreds of thousands or millions of light-years away. This feedback from supermassive black holes appears to be crucial in regulating galaxy formation and evolution. Galaxies with the most massive central black holes tend to have the largest stellar masses and show less active star formation. This suggests a connection. As a supermassive black hole grows, it increasingly suppresses star formation in its host galaxy, eventually quenching star formation almost entirely. The galaxy becomes red and dead, filled with old red stars but forming few, if any, new ones. Without black hole feedback, galaxies would convert far more of their gas into stars, and the universe would look very different. The relationship between supermassive black holes and their host galaxies extends to a striking correlation between the black hole's mass and properties of the galaxy's central stellar bulge. Across many orders of magnitude in mass, from galaxies with modest black holes to those with the most massive ones, there's a tight relationship between the black hole mass and both the mass and velocity dispersion of stars in the galaxy's bulge. This suggests that black holes and galaxies don't evolve independently, but co-evolve, influencing each other's growth in ways we're still working to understand fully. Some supermassive black holes produce jets of truly cosmic proportions. The black hole at the center of Messier 87, the one first imaged by the Event Horizon Telescope, produces a jet that extends for at least 5,000 light-years from the galaxy, blazing brilliantly in radio waves. Other galaxies have jets stretching for hundreds of thousands or even millions of light-years, in some cases spanning distances larger than the entire Milky Way galaxy. These jets appear to be powered by the black hole's rotation, extracting energy from the hole's spin through complex interactions with magnetic fields threading through the accretion disk. As you breathe slowly and deeply, picture yourself at the center of a galaxy, near one of these supermassive black holes. You're far enough away to be safe, perhaps orbiting just outside the accretion disk's outer edge. Looking inward, you see the disk glowing in brilliant shades of blue and violet, compressed and heated to millions of degrees. The light is so intense it hurts to look at directly. Closer to the black hole, the disk glows in X-rays invisible to your eyes, but felt as searing heat. And at the very center, you see the black hole's shadow, a perfect circle of absolute darkness where no light can escape, the event horizon silhouetted against the glowing disk. The black hole's gravity is so strong that it bends light from behind it, creating a halo around the shadow. You're witnessing one of nature's most spectacular sights, a supermassive black hole actively feeding on the matter around it. These central engines, hidden in darkness yet shining with the light of billions of suns when they feed, have shaped the universe we inhabit. They've regulated star formation, influenced galaxy shapes and sizes, and created some of the most energetic phenomena we observe. They're both creators and destroyers, building galaxies while simultaneously preventing unlimited star formation. They are testament to the universe's ability to take gravity to its absolute extreme, creating objects so massive and so dense that they warp space-time into permanent features from which nothing can return. Intermediate mass black holes, the missing link. Between the stellar mass black holes formed from collapsing stars and the supermassive giants anchoring galaxies lies a mysterious middle ground. Intermediate mass black holes. These objects, with masses roughly between 100 and 100,000 times that of our Sun, were once thought not to exist at all. They were the missing link in black hole populations, and their rarity has puzzled astronomers for decades. The problem is this. We understand reasonably well how stellar mass black holes form. Massive stars collapse, creating black holes of a few to perhaps 100 solar masses. We also know that supermassive black holes exist in galactic centers with masses of millions to billions of solar masses. But the region in between, the intermediate mass range, appears strangely empty. There should be a continuum of black hole masses if black holes can grow over time, yet observations have found relatively few candidates in this intermediate range. Why are intermediate mass black holes so rare? Part of the answer relates to formation mechanisms. Stellar collapse typically can't produce black holes more massive than about 65 solar masses because of the pair instability supernova phenomenon. Stars in the right mass range simply explode completely rather than leaving a remnant behind. And the processes that build supermassive black holes, whether starting from seed black holes or through direct collapse of gas clouds, seem to favor jumping straight to higher masses rather than lingering in the intermediate range. Another factor is the environment. If intermediate mass black holes form, they likely do so in the dense cores of star clusters, where many stars crowd together in a relatively small volume. In such environments, stellar interactions are common. Stars can collide and merge, creating more massive stars that might then collapse to form more massive black holes than would be possible from single stars. Or stellar mass black holes themselves might merge, combining their masses into progressively larger black holes. This process of runaway merging could build black holes of thousands of solar masses in the centers of dense star clusters. But these same dense environments can also eject black holes. When two massive objects merge or interact closely, conservation of momentum can kick one or both of them out of the cluster at high velocity. An intermediate mass black hole might form in a cluster's core only to be ejected into the wider galaxy, where it would be difficult to detect unless it happens to accrete gas or pass close to a star. For decades, intermediate mass black holes remained hypothetical, with only a handful of tentative candidates. Some ultraluminous X-ray sources, objects too bright to be explained by stellar mass black holes but found away from galactic centers, were proposed as possible intermediate mass black holes accreting matter. But these interpretations were uncertain, with alternative explanations possible. The situation changed dramatically with gravitational wave astronomy. On May 21, 2019, the LIGO and Virgo detectors recorded a gravitational wave signal designated Chido Anhaino 21. This signal was different from most previous detections. It was brief, only 4 short wiggles lasting less than 1/10 of a second, compared to the longer chirps of lighter black hole mergers. Analysis revealed that this signal came from the merger of 2 black holes with masses of about 85 and 66 times the Sun's mass. Both of these black holes were unusual. The 85 solar mass black hole fell right in the pair instability mass gap, the range where single stars shouldn't be able to create black holes. This strongly suggested it formed from an earlier merger of smaller black holes. But even more remarkable was the merger product. The 2 black holes combined to create a single black hole, with a mass of about 142 times that of the Sun, firmly in the intermediate mass range. This was the first clear detection of an intermediate mass black hole, and it proved they could exist. Since then, more detections have followed. In November 2023, the LIGO-Virgo-Kagra collaboration detected GW23123, produced by the merger of black holes with masses around 100 and 140 solar masses. The resulting black hole weighed approximately 225 solar masses, making it the most massive black hole merger detected through gravitational waves to date. Both progenitor black holes were spinning rapidly and had masses that suggest they too formed through earlier mergers. These detections point to a hierarchical merger scenario. Small stellar mass black holes merge in to create larger stellar mass black holes. These merge with other black holes to create ones at the upper end of the stellar mass range or crossing into the intermediate mass range. These can merge again, building black holes of hundreds of solar masses. Each generation of mergers adds mass and can increase spin, creating black holes that couldn't form any other way. This hierarchical merging is likely most efficient in dense stellar environments. Globular clusters, ancient spherical collections of hundreds of thousands to millions of stars, all formed at roughly the same time, provide ideal conditions. These clusters are so dense that in their cores, stars are separated by distances comparable to our solar system's size. In such tight quarters, black holes can find each other and merge over relatively short timescales. Some globular clusters do show evidence for intermediate mass black holes. By measuring how stars move in a cluster's center, astronomers can infer the total mass in that region. In a few cases, this central mass appears too large to be explained by the visible stars alone, suggesting an invisible, massive object might lurk there. One candidate is in Messier 4, the closest globular cluster to Earth, where observations suggest a central mass of several hundred to about 800 solar masses concentrated in a very small region. Another promising candidate was found using the Hubble Space Telescope in a galaxy about 740 million light-years away. Designated 3XMM J215245-8, this object appears to be an intermediate mass black hole of about 50,000 solar masses. It was discovered through its X-ray emission, suggesting it's actively accreting matter. The X-ray properties are consistent with a black hole in this mass range, though as with many candidates, some uncertainty remains. Intermediate mass black holes might also exist in dwarf galaxies, small galaxies with perhaps a few billion stars or less. If the relationship between galaxy mass and central black hole mass extends to these smaller systems, dwarf galaxies should contain intermediate mass black holes rather than supermassive ones. Finding and confirming these would help us understand whether the scaling relationship holds across all galaxy sizes, and could provide insights into how supermassive black holes first formed. The importance of intermediate mass black holes extends beyond simply filling in the mass spectrum. They're crucial for understanding how supermassive black holes grow. If supermassive black holes build up through mergers of intermediate mass black holes, then finding these intermediate objects and studying their properties and populations helps us piece together the evolutionary pathway from stellar mass to supermassive. They also serve as laboratories for understanding black hole physics in a regime we haven't studied extensively. Intermediate mass black holes are large enough that their event horizons are substantial, making certain quantum effects negligible, but small enough that they evolve more quickly than supermassive black holes. They might help bridge our understanding between the well-studied stellar mass black holes and the supermassive ones. As gravitational wave detectors become more sensitive and new facilities come online, we'll likely detect many more intermediate mass black hole mergers. Space-based gravitational wave observatories, which will be sensitive to lower frequencies than ground-based detectors, should be able to detect mergers of more massive intermediate mass black holes and perhaps even capture the merger of intermediate mass black holes with supermassive ones. Each detection adds another piece to the puzzle, helping us understand how black holes of all masses fit together in a cosmic hierarchy. Picture, as you relax into sleep, these intermediate mass black holes scattered through the universe. Some lurk in the dense cores of star clusters, surrounded by ancient stars. Others orbit in the outskirts of galaxies, ejected from their birthplaces. Still others spiral together in pairs, destined to merge and send gravitational waves rippling across the cosmos. They're the bridges between the small and the giant, the rungs on a ladder that reaches from single dying stars to the massive hearts of galaxies. They're proof that the universe builds complexity through steps, accumulating mass through merger after merger, generation after generation. Primordial black holes, ghosts of the early universe. We now journey to the very beginning of time itself, to the first fraction of a second after the Big Bang, when the universe was unimaginably hot and dense and perhaps strange enough to forge black holes directly from the cosmic fireball. These are primordial black holes, and unlike all the other types we've discussed, they wouldn't form from the collapse of stars or the merging of existing black holes. They might have formed directly from the raw energy and matter of the infant universe. To understand primordial black holes, we need to go back 13.8 billion years, to the moment of the Big Bang. In the first instant after the universe began, it was far smaller than an atom, yet contained all the energy and matter that would eventually expand to fill the cosmos we see today. The temperature was so high that matter as we know it couldn't exist. There were no atoms, no nuclei, not even protons or neutrons. Instead, there was a seething soup of quarks, gluons, and other fundamental particles, all at energies far beyond anything we can recreate in our most powerful particle accelerators. The very early universe was also remarkably smooth and uniform, but not perfectly so. Quantum fluctuations, tiny random variations in energy density that arose from the Heisenberg uncertainty principle, were stretched to macroscopic scales by cosmic inflation, a brief period of exponential expansion that occurred in the first fraction of a second. These fluctuations created regions that were slightly denser than average and regions that were slightly less dense. In the first second after the Big Bang, while the universe was still extraordinarily dense by any standard we can comprehend, some of these overdense regions might have been dense enough to collapse under their own gravity and form black holes. Unlike stellar collapse, which requires a star to exhaust its fuel and lose the pressure support that holds it up, these primordial black holes could form directly from the compression of the early universe's matter and energy. The mass of a primordial black hole would depend on when it formed. In the very earliest moments, when the universe's density was at its highest, even a tiny region collapsing would create a minuscule black hole. As the universe expanded and its density decreased, larger regions would be needed to create a black hole, resulting in more massive primordial black holes. Depending on exactly when they formed within that first second, primordial black holes could span an enormous range of masses, from far less than a grain of sand to hundreds of thousands of times the mass of the Sun. The smallest primordial black holes would be truly tiny, microscopic by any reasonable definition. A black hole with the mass of an asteroid might have an event horizon smaller than a single atom. Despite their small size, these would still be genuine black holes, with all the properties that entails. They would warp space-time around them, have event horizons from which nothing can escape, and obey the same laws of physics as their stellar mass and supermassive cousins. But here's where things get interesting. In 1974, Stephen Hawking made a groundbreaking discovery. He showed that black holes aren't entirely black. Due to quantum effects near the event horizon, black holes emit radiation, now called Hawking radiation. This radiation causes black holes to lose mass over time, slowly evaporating. The rate of evaporation is inversely proportional to the black hole's mass. Massive black holes evaporate so slowly that they would take far longer than the current age of the universe to disappear. But small black holes evaporate quickly. Hawking calculated that a black hole with the mass of a mountain would take about as long as the current age of the universe to evaporate. Smaller primordial black holes, those with less mass than a mountain, would evaporate more rapidly. The smallest ones, those that formed in the very earliest moments and had the least mass, would have evaporated long ago, perhaps within the first few seconds or minutes after the Big Bang. Medium-sized primordial black holes might be evaporating right now, after 13.8 billion years. Larger ones would persist far into the future. This means that if primordial black holes formed across a range of masses, the smallest ones are already gone, evaporated completely. The ones evaporating now would emit a final burst of gamma rays as they disappear, potentially detectable by our satellites. And the larger ones, if they exist, would still be out there, dark and invisible unless they happen to interact with matter around them. The possibility of primordial black holes has fascinated physicists for decades because they might explain one of the deepest mysteries in cosmology: dark matter. Observations of galaxy rotation, gravitational lensing, the cosmic microwave, background, and other phenomena all point to the existence of dark matter, an invisible form of matter that makes up about 85% of all matter in the universe. We know dark matter exists because we can see its gravitational effects, but we don't know what it is. Numerous experiments have searched for exotic particles that might make up dark matter, but none have succeeded in detecting them. Primordial black holes could potentially be dark matter. If primordial black holes formed with certain masses, particularly in the range from about the mass of an asteroid to thousands of solar masses, they would persist until the present day. They would be completely dark, emitting no light of their own. They would interact with ordinary matter only through gravity, and they would be spread throughout space, including in the halos surrounding galaxies where dark matter is known to exist. For a while, this seemed like a promising idea. But as observations improved, constraints tightened. If primordial black holes in certain mass ranges made up a significant fraction of dark matter, they should have observable effects that we don't see. They should gravitationally lens background stars more often than observed. They should alter the distribution of matter in the early universe in ways that would leave imprints on the cosmic microwave background that aren't there. They should affect the dynamics of stellar systems in ways we don't observe. These constraints have ruled out primordial black holes as the dominant component of dark matter for most mass ranges. There are still some windows, some mass ranges where primordial black holes could exist in significant numbers without violating observational constraints, but they couldn't make up all or even most of dark matter. The dream of explaining dark matter with primordial black holes has faded, though it hasn't entirely disappeared. But primordial black holes might still exist even if they're not dark matter. They could be rare, making up only a small fraction of the total matter density, yet still present in the universe. Some of the intermediate mass black holes detected through gravitational waves might actually be primordial rather than formed through stellar processes and mergers. This would be difficult to prove definitively, but the possibility is tantalizing. Primordial black holes might also have played a role in forming the first supermassive black holes. If primordial black holes with masses of thousands or tens of thousands of solar masses formed in the early universe, they could serve as the seeds from which supermassive black holes grew. This would help explain how billion solar mass black holes existed when the universe was less than 1 billion years old. Starting with a substantial seed mass makes the growth to supermassive proportions much more feasible. Finding evidence for primordial black holes is challenging because they're so difficult to distinguish from black holes formed through other processes. A stellar mass primordial black hole would look identical to a stellar mass black hole formed from a collapsing star. The only differences might be in their distribution in space or in slight variations in their properties that could hint at a different origin. One possible signature is in their abundance in galactic halos versus in stellar regions. Black holes formed from stars should be concentrated where stars are, in galaxy disks and bulges. Primordial black holes, formed in the early universe before galaxies existed, might have a different spatial distribution, spread more uniformly through the dark matter halo surrounding each galaxy. Another possibility is finding black holes in mass ranges that are difficult to explain through stellar processes. If gravitational wave detectors find numerous black holes with masses of a few solar masses or less, masses too small to form through stellar collapse, but too large to have evaporated through Hawking, radiation that might hint at a primordial origin. As your mind drifts toward sleep, imagine the very early universe, a fraction of a second old, far smaller and denser than it is today. Tiny fluctuations in density, quantum ripples expanded to cosmic scales, collapse here and there, creating black holes directly from the primordial fireball. Most are small, destined to evaporate quickly. Some are larger, persisting through the ages. Fast forward 13.8 billion years. These primordial black holes, if they exist, are scattered through the cosmos, ancient relics from the universe's first moment, invisible ghosts that have witnessed all of cosmic history. They're the universe's first-born structures, predating stars, galaxies, and all the complexity that would emerge in the eons to follow. Rotating black holes. The Kerr solution. Until now, we've discussed black holes primarily in terms of their mass, but black holes have another crucial property. They can rotate. In fact, rotation is so fundamental to black holes that it changes their structure, their properties, and their effects on surrounding space-time in profound ways. Understanding rotating black holes takes us deeper into the strange physics that governs these objects and reveals possibilities that non-rotating black holes simply don't possess. In 1963, a New Zealand mathematician named Roy Kerr found an exact solution to Einstein's equations that described a rotating black hole. This was a major breakthrough. Einstein's equations are notoriously difficult to solve, and finding exact solutions is rare. The Schwarzschild solution, describing a non-rotating black hole, had been known since 1916, but the rotating case proved far more challenging. Kerr's solution opened up a new understanding of what black holes could be. The Kerr solution, as it's now called, describes a black hole characterized by just two properties, its mass and its angular momentum, a measure of how fast it's rotating. This simplicity is remarkable. The no-hair theorem, proven in the 1970s, states that black holes are uniquely determined by only three properties: mass, charge, and angular momentum. In realistic astrophysical situations, black holes have negligible electric charge because any charge would quickly be neutralized by attracting opposite charges. So, real black holes are described entirely by their mass and spin. Angular momentum in black holes comes from the rotation of the matter that collapsed to form them. Stars rotate, and when a rotating star collapses, conservation of angular momentum means the rotation speeds up dramatically, just as a figure skater spins faster when pulling their arms in. A black hole formed from a rotating star inherits that rotation, and it can spin at enormous rates. There's a maximum rate at which a black hole can spin, set by general relativity itself. This maximum spin is characterized by a parameter astronomers call A, which is related to the black hole's angular momentum divided by its mass. For a non-rotating black hole, A equals 0. As rotation increases, A increases, approaching a maximum value of 1. A black hole with A equal to 1 is called an extremal or maximally rotating Kerr black hole. At maximum rotation, the black hole's event horizon shrinks to half the size it would have if it weren't rotating. The singularity is no longer a point, but rather a ring, lying in the equatorial plane. And new regions of spacetime emerge that have no analog in non-rotating black holes. The most important of these new features is the ergosphere. This is a region outside the event horizon where spacetime is dragged around by the black hole's rotation so strongly that nothing, not even light, can remain. Stationary. Everything in the ergosphere must rotate in the same direction as the black hole, though it's still possible to escape from the ergosphere, unlike from inside the event horizon. The ergosphere's outer boundary is called the static limit, and it touches the event horizon at the black hole's poles, but extends farther out at the equator. The dragging of spacetime by a rotating mass is called frame dragging, or the Lenz-Thirring effect, named after the physicists who first predicted it. Earth's rotation drags spacetime around it very slightly, an effect that was measured by the Gravity Probe B satellite after decades of effort. Near a rapidly rotating black hole, frame dragging becomes extreme. Space itself is pulled around in a whirlpool around the spinning black hole. This frame dragging has observable consequences. Matter orbiting a rotating black hole can orbit in the same direction as the black hole's spin, a prograde orbit, or opposite to it, a retrograde orbit. Because spacetime itself is moving in the prograde direction. A prograde orbit can be closer to the black hole and more tightly bound than a retrograde orbit. This means the innermost stable circular orbit, the closest distance at which matter can orbit without spiraling in, depends on the black hole's spin and on whether the orbit is prograde or retrograde. For a non-rotating black hole, the innermost stable circular orbit is at 3 times the Schwarzschild radius, about 9 kilometers from the singularity for a solar mass black hole. For a maximally rotating black hole, the prograde innermost stable orbit can be much closer, almost at the event horizon itself. This has important implications for accretion disks. In a disk around a rapidly spinning black hole, matter can get much closer before falling in, reaching higher velocities and temperatures, potentially emitting more energetic radiation. The ergosphere also enables a remarkable possibility, extracting energy from a rotating black hole. In 1969, the physicist Roger Penrose showed that it's theoretically possible to use the ergosphere to extract rotational energy from a black hole. The process, now called the Penrose process, works like this. Imagine you drop an object into the ergosphere. Inside the ergosphere, It's possible for the object to split into two pieces in such a way that one piece has negative energy, as measured by an outside observer. This negative energy piece falls into the black hole, reducing the black hole's mass and rotational energy. The other piece escapes with more energy than the original object had. This might sound like magic, but it's a consequence of how energy is defined in the strange space-time around a rotating black hole. The black hole's rotation provides the energy that the escaping piece gains. Over time, such a process could slow a black hole's rotation, converting its rotational energy into useful work. An advanced civilization might, in principle, use this to power themselves by extracting energy from a spinning black hole. A more realistic version of energy extraction involves magnetic fields in the accretion disk. The Blandford-Znajek process, proposed in 1977, describes how rotating black holes can power the tremendous jets observed in active galactic nuclei and some stellar mass black hole systems. Magnetic field lines threading through the ergosphere can extract rotational energy from the black hole, channeling it into the jets that blast outward at nearly the speed of light. This mechanism might be responsible for some of the most energetic phenomena in the universe, quasars and blazars that outshine entire galaxies. Astronomers can measure black hole spins through several methods. One involves studying the X-ray emission from the inner edge of the accretion disk. The disk's inner edge is at the innermost stable circular orbit, and its location depends on the black hole's spin. By carefully analyzing the spectrum of X-rays, particularly looking at features from iron atoms in the disk, astronomers can infer where the inner edge is, and thus determine the black hole's spin. Another method uses gravitational waves. When two black holes merge, the gravitational waves they emit carry information about both black holes' spins. The waveform, the pattern of how the gravitational wave frequency and amplitude change with time, depends on the masses and spins of both black holes. By carefully matching observed waveforms to theoretical predictions, scientists can measure the spins. These measurements have revealed that black holes span a wide range of spins. Some are slowly rotating, with spin parameters much less than 1. Others are rapidly rotating, with spins approaching the maximum. The distribution of spins provides clues about how black holes form and grow. Black holes that grow primarily through accretion tend to spin up over time because the accreting matter carries angular momentum that gets transferred to the black hole. Black holes that grow through mergers might end up with various spins depending on the spins and orbital configurations of the merging black holes. The first black hole ever imaged, the supermassive black hole in Messier 87, appears to be rotating, though the exact spin rate isn't yet precisely determined. The observed jet, stretching thousands of light-years, is likely powered by the black hole's rotation through the Blandford-Znajek process. The jet's power is immense, equivalent to the luminosity of billions of suns, all extracted from the rotational energy of the central black hole. Rotating black holes also have more complex internal structures than non-rotating ones. Inside the event horizon of a Kerr black hole, there's an inner horizon called the Cauchy horizon. Between the outer and inner horizons lies a region where, theoretically, some unusual things could happen. The mathematics suggests instabilities and infinities at the Cauchy horizon that render our predictions uncertain. Most physicists suspect that in a realistic black hole formed from collapse, quantum effects or the presence of any infalling matter would make the region near the Cauchy horizon unstable, and unlike the idealized Kerr solution. There's also the question of whether black holes can be spun faster than the maximum. The cosmic censorship hypothesis, proposed by Roger Penrose, suggests that naked singularities not hidden behind an event horizon, cannot exist in nature. If you could spin up a black hole past the maximum, the event horizon would disappear, exposing the singularity. Most attempts to overspin a black hole through thought experiments seem to fail. The black hole resists being spun faster than the limit, either by ejecting the excess angular momentum or by preventing the overspinning matter from reaching the event horizon. As you settle into deeper relaxation, picture a black hole spinning at nearly the maximum rate. Its event horizon is stretched into an oblate shape, flattened at the poles and bulging at the equator. Around it, the ergosphere shimmers like a ghostly shell, a region where space itself whirls in an irresistible current. The accretion disk spirals down to almost the event horizon before vanishing within, glowing brilliantly with the energy of infalling matter, heated to billions of degrees. From the poles, jets of plasma shoot outward at 99% the speed of light, cosmic searchlights powered by the black hole's spin. This is a rotating black hole, a cosmic dynamo, turning spacetime itself into an energy source, a testament to the universe's ability to create structures of sublime complexity and power. The physics of black holes. Deeper mysteries. Let's delve deeper now into the physics that makes black holes so fascinating and so strange. We've touched on event horizons and singularities, rotation and ergospheres, but there's much more to explore about how black holes interact with their environment and what happens in their vicinity. Accretion disks are perhaps the most important feature for detecting and studying black holes. When matter falls toward a black hole, it rarely falls straight in. Usually, the matter has some angular momentum, some sideways motion relative to the black hole. Conservation of angular momentum means this matter must orbit the black hole, and as more matter accumulates, it forms a disk. This disk is not a solid object, but rather a vast swarm of gas, dust, and plasma, all orbiting the black hole at different speeds depending on distance. Material closer to the black hole orbits faster, while material farther out orbits more slowly, following Kepler's laws, just as planets orbit the Sun at different speeds based on their distance. But unlike planets, which orbit in isolation, the particles in an accretion disk constantly collide and interact with each other. These interactions create friction. When faster-moving inner material rubs against slower-moving outer material, kinetic energy is converted to heat. This frictional heating is enormously efficient. The inner regions of an accretion disk around a stellar mass black hole can reach temperatures of tens of millions of degrees. At such temperatures, the disk glows in X-Ow rays. Around supermassive black holes, the inner disk might be somewhat cooler, but still hot enough to emit ultraviolet and X-ray light. The friction also causes angular momentum to be transferred outward through the disk. Material loses angular momentum and spirals inward, while the angular momentum itself migrates outward. This allows matter to gradually work its way from the disk's outer regions to its inner edge, and eventually fall into the black hole, feeding it and causing it to grow. The innermost stable circular orbit marks the disk's inner edge. Inside this orbit, there are no stable circular paths. Matter crossing inward from the innermost stable orbit quickly plunges into the event horizon, typically within a fraction of a second for stellar mass black holes, or a few minutes to hours for supermassive black holes. This plunging material doesn't have much time to emit additional radiation, so most of the disk's luminosity comes from the region just outside the innermost stable orbit. Some black holes, particularly stellar mass black holes in binary systems and supermassive black holes in active galactic nuclei, produce jets. These are narrow beams of particles, primarily electrons and positrons moving at close to the speed of light, shot outward perpendicular to the accretion disk. The jets can extend for vast distances, thousands of light years for stellar mass black holes and millions of light years for supermassive black holes. The exact mechanism for launching jets is still not fully understood, but it involves magnetic fields threading through the accretion disk and the black hole's ergosphere. These magnetic fields can tap into the rotational energy of the black hole or the orbital energy of the disk, accelerating particles to extreme velocities and confining them into narrow beams. The Blandford-Zanajek process we discussed earlier is one proposed mechanism, but the details involve complex magnetohydrodynamics that challenge even supercomputer simulations. Jets can have profound effects on their environment. When a jet from a supermassive black hole plows into the surrounding intergalactic gas, it creates enormous bubbles of hot plasma, visible in radio and X-ray observations. These bubbles can be larger than the entire galaxy, containing as much energy as the explosion of billions of supernovae. The energy deposited by jets heats gas over vast volumes, preventing it from cooling and forming stars, fundamentally altering galaxy evolution. Now, imagine what would happen if you could somehow fall into a black hole. Let's assume for this thought experiment that you're falling into a supermassive black hole, where the tidal forces at the event horizon are gentler than for a stellar mass black hole. As you approach the event horizon, you would first notice time dilation. Clocks moving through strong gravitational fields run slower, as measured by distant observers. As you fall, your clock would appear to tick more and more slowly to someone watching from far away. Light from you would become increasingly redshifted, dimmer and redder, until you appear to fade away and freeze at the event horizon, never quite crossing. But that's the view from outside. From your perspective, falling in, things are very different. You don't notice anything special when you cross the event horizon. There's no barrier, no wall, no sensation marking that you've passed the point of no return. If the black hole is large enough, the tidal forces at the horizon are weak enough that you might not feel anything unusual at all. You would simply continue falling inward. However, tidal forces grow stronger as you approach the singularity. Tidal forces arise because gravity gets stronger the closer you are to a massive object. Your feet, if you're falling feet first, are closer to the singularity than your head, so they experience stronger gravity. They are pulled harder than your head, stretching you. At the same time, the gravitational field is also pulling you together from the sides, compressing you. This stretching lengthwise and compressing crosswise is called spaghettification, and it's how tidal forces will eventually destroy any object falling into a black hole. For a stellar mass black hole, spaghettification would occur well before you reach the event horizon. You'd be torn apart by tidal forces while still outside. But for a supermassive black hole with 1 billion solar masses, the event horizon is so far from the singularity that tidal forces there are relatively gentle. You could cross the horizon intact and survive for a while longer as you fall toward the singularity. Eventually, of course, as you get closer to the singularity, the tidal forces would become infinite and you would be destroyed. But you might have time to look around, to observe the strange environment inside the event horizon. What would you see? Light can fall into a black hole, so you could still see things. Looking outward, you might see the universe outside, though distorted by the extreme curvature of space-time. As you fall, the outside universe might appear to speed up, time dilation now working in reverse from your perspective. In principle, you could watch billions of years of cosmic history pass by as you take your final plunge. Looking inward, toward the singularity, things become difficult to predict, because we don't know what happens at the singularity itself. There's also a fascinating question about information. According to quantum mechanics, information about the state of a system cannot be destroyed. If you know the complete state of a system at one time, you can, in principle, calculate its state at any future or past time. But when something falls into a black hole, it seems like the information about what fell in is lost forever. The black hole's properties, its mass, charge, and spin, increase by predictable amounts, but all the detailed information about what actually fell in seems to disappear. This is the black hole information paradox, and it's one of the deepest puzzles in theoretical physics. Hawking's work on black hole radiation intensified the paradox. If black holes evaporate completely through Hawking radiation, and if that radiation is purely thermal, carrying no information about what fell in, then information has been destroyed, violating quantum mechanics. Many solutions have been proposed, from suggestions that information is encoded in subtle correlations in the Hawking radiation, to ideas that information is preserved in remnants left behind after evaporation. Recent work suggests that information might indeed be preserved in the Hawking radiation, though the exact mechanism is still debated. Black holes also have thermodynamic properties. In 1973, Jacob Bekenstein proposed that black holes have entropy, a measure of disorder or information content. He showed that a black hole's entropy is proportional to the area of its event horizon, not its volume. This was revolutionary because it suggested a deep connection between gravity, quantum mechanics, and thermodynamics. Hawking's calculation of black hole radiation strengthened this connection. Hawking radiation allows black holes to have a temperature. Smaller black holes are hotter, while larger ones are cooler. A solar mass black hole has a temperature of about 1/10,000,000th of a degree above absolute zero, far colder than the cosmic microwave background radiation filling space. But a black hole with the mass of a mountain would have a temperature of about room temperature, and smaller ones would be hotter still. These thermodynamic properties suggest that black holes are not just gravitational objects, but also quantum objects. The entropy being proportional to area rather than volume hints that the fundamental degrees of freedom might somehow be located on the event horizon rather than throughout the volume, an idea that has led to the holographic principle and important developments in string theory and quantum gravity. As your breathing becomes deeper and slower, as you drift closer to sleep, picture the black hole not as a simple object, but as a nexus where multiple mysteries intersect. It's where gravity becomes so strong that space-time itself folds up. It's where quantum mechanics and general relativity meet and create paradoxes we're still working to resolve. It's where thermodynamics takes on new meanings, with temperature and entropy defined in strange new ways. Black holes are laboratories for physics at its most fundamental, natural experiments that push our theories to their limits and reveal where our understanding still falls short. Hawking radiation and black hole evaporation. In the early 1970s, Stephen Hawking made one of the most profound discoveries in theoretical physics. He showed that black holes, despite their name, aren't entirely black. They emit radiation, and over immense timescales, this radiation will cause even the largest black holes to evaporate completely, vanishing in a final burst of energy. This discovery linked quantum mechanics and general relativity in an unexpected way, and opened up entirely new questions about the nature of black holes and the universe. To understand Hawking radiation, we need to think about quantum mechanics and empty space. In quantum theory, even the vacuum of space is not truly empty. It seethes with quantum fluctuations, temporary violations of energy conservation allowed by Heisenberg's uncertainty principle. These fluctuations can be thought of as pairs of virtual particles, a particle and its antiparticle constantly appearing and disappearing everywhere in space. Normally, these particle pairs exist for such a brief instant that they have no observable effects. They pop into existence, exist for a time so short it's barely meaningful to say they existed at all, and then annihilate each other and disappear. Near a black hole's event horizon, these quantum fluctuations can have a dramatic effect. If a particle-antiparticle pair appears just outside the event horizon, it's possible for one member of the pair to fall into the black hole while the other escapes. To an outside observer, it appears that the black hole has emitted a particle. This is Hawking radiation. Now, there's a subtlety here. The common explanation, involving one particle falling in and one escaping, was popularized by Hawking himself, but it's somewhat misleading. The actual physics is more subtle, involving quantum field theory in curved spacetime. The gravitational field near the event horizon affects how we define what we mean by a particle in quantum field theory. What an observer far from the black hole perceives as a vacuum, empty space, differs from what an observer falling into the black hole perceives. This difference in perspective leads to the emission of radiation. But the result is clear. To a distant observer, the black hole emits particles, primarily photons, with a thermal spectrum. The radiation has a temperature inversely proportional to the black hole's mass. Massive black holes are cold, while tiny black holes are hot. For a black hole with the mass of our Sun, the temperature is about 60 nanokelvins, 60 billionths of a degree above absolute zero. This is far colder than the cosmic microwave background radiation, which is about 3 degrees above absolute zero. Such a black hole would actually absorb more radiation from the background than it emits, so it would grow rather than shrink. Only when the cosmic microwave background temperature drops sufficiently in the distant future as the universe continues. Expanding and cooling, would solar mass black holes begin to evaporate. But for smaller black holes, the temperature is higher. A black hole with the mass of the Moon would have a temperature of a few degrees, comparable to the current cosmic microwave background. A black hole with the mass of a mountain would be at room temperature, around 300 degrees above absolute zero. And a black hole with the mass of a large asteroid would be extremely hot, thousands of degrees or more. The power emitted through Hawking radiation is also inversely proportional to the square of the black hole's mass. Massive black holes emit very little power, while tiny black holes emit tremendous amounts. A solar mass black hole emits less than 100 trillionth of a watt, utterly negligible. But a black hole with a mass of a few 100 million kilograms, about the mass of a large mountain, would emit about the same power as a large electrical power plant. This leads to a runaway process. As a black hole emits radiation, it loses energy, and since energy and mass are equivalent through Einstein's E equals mc squared, it loses mass. As it loses mass, it gets hotter and emits radiation faster, losing mass even more quickly. The process accelerates. A black hole shrinks slowly at first, but as it gets smaller, the evaporation rate increases exponentially. For very large black holes, this process takes unimaginable amounts of time. A solar mass black hole would take about 10 to the power of 67 years to evaporate completely. That's 10 million trillion 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 years. Far, far longer than the current age of the universe of 13.8 billion years. A supermassive black hole with a billion solar masses would take more than 10 to the power of 94 years. A 1 followed by 94 zeros. But smaller black holes evaporate much faster. A black hole with the mass of the Moon would take about 10 to the power of 36 years. A mountain mass black hole would evaporate in about 10 billion years, comparable to the current age of the universe. And the smallest primordial black holes, if they formed with masses around 10 to the power of 15 grams, about the mass of a large asteroid, would be evaporating right now, 13.8 billion years after the Big Bang. The final moments of a black hole's evaporation are spectacular, at least in theory. As the black hole shrinks to microscopic size, its temperature becomes immense. It glows white-hot, then blue, emitting gamma rays and other high-energy particles at a tremendous rate. In the last fraction of a second, the remaining mass is converted almost entirely to radiation in a final explosive burst. For a brief instant, this tiny evaporating black hole would shine more brightly than a star, then vanish completely, leaving behind only a flash of light and particles. No one has ever observed a black hole evaporate, of course. The rate is far too slow for any black hole we can detect. But astronomers have searched for the gamma-ray bursts that would mark the final explosion of small primordial black holes. So far, none have been definitively detected, which places constraints on how many such black holes can exist. Hawking radiation raises deep questions about quantum mechanics and information. If a black hole evaporates completely, what happens to the information about everything that fell into it? Does the information emerge somehow in the Hawking radiation? Does it get destroyed, violating quantum mechanics? Or does something else happen? This information paradox has driven decades of research and led to insights about quantum gravity, the holographic principle, and the fundamental nature of space-time. In the far future, in the very far future, black holes will be among the last structures remaining in the universe. Stars will have long since exhausted their fuel. Galaxies will have dispersed, and the universe will be dark and cold. But black holes will persist, slowly evaporating through Hawking radiation. The smallest will evaporate first, then progressively larger ones over timescales that dwarf the current age of the universe. Eventually, even the supermassive black holes will evaporate, leaving behind only a diffuse sea of radiation in an expanding, cooling cosmos. Picture this future as you relax, a universe incomprehensibly old, dark, and empty. Here and there, the occasional flash marks a black hole's final moment, a brief spark in the darkness. Eventually, even these will cease. The black holes, the last remnants of stars and galaxies, will have evaporated away, their mass and energy dissipated into the cosmic void. It's a future of ultimate entropy, of equilibrium, of quiet darkness, but also a testament to the strange quantum processes that ensure nothing, not even a black hole, lasts forever. Detecting black holes are windows into darkness. Black holes are, by definition, dark. They emit no light of their own, and light that falls in never comes back out. So, how do we detect and study objects that are invisible? The answer lies in observing their effects on their surroundings and on the fabric of space-time itself. Over the decades, astronomers have developed multiple methods for finding black holes and measuring their properties, each revealing different aspects of these fascinating objects. The first black holes to be discovered were found through X-ray astronomy. In the 1970s, satellites carrying X-ray detectors began surveying the sky. Among the X-ray sources they found were several that flickered rapidly and emitted enormous amounts of X-ray energy. When astronomers studied these sources in other wavelengths, they often found binary star systems, a visible star orbiting an invisible companion. By measuring the visible star's orbital motion, astronomers could determine the mass of the invisible companion using Kepler's laws. In several cases, the invisible object was too massive to be a neutron star. The most massive neutron stars can be at most about 2 to 2.5 solar masses. Any compact object more massive than this must be a black hole, as there's no other known object that could be so massive yet so compact and dark. These X-ray binary systems revealed stellar mass black holes actively feeding on matter pulled from their companion stars. The X-rays come from the accretion disk, gas swirling around the black hole and heating up to millions of degrees before falling in. By studying the X-ray emission in detail, astronomers could learn about the black hole's mass, its spin, the geometry of the accretion disk, and the physical processes occurring near the event horizon. For supermassive black holes, a different method proved crucial. In the 1970s and 80s, astronomers began using spectroscopy to measure the velocities of stars and gas near the centers of galaxies. They found that in many galaxies, stars near the center were moving at very high velocities, far faster than could be explained by the visible stars and gas alone. Something massive and invisible had to be present to gravitationally accelerate these stars to such speeds. The most detailed study has been of our own galaxy's center. Starting in the 1990s, astronomers using large telescopes equipped with adaptive optics and infrared cameras began tracking individual stars orbiting the Milky Way's center. These stars, particularly one called S2 or SO2, orbit something invisible in elliptical paths, sometimes coming within just a few light hours of the central object. By precisely measuring these orbits over decades, astronomers determined that the central object has about 4 million times the Sun's mass and is concentrated in a region smaller than our solar system. The only explanation is a supermassive black hole, Sagittarius A. Kerr. This method of using stellar orbits has been applied to other galaxies as well. By measuring how fast stars or gas move at different distances from a galaxy's center, astronomers can infer the central mass distribution. In most large galaxies, the velocities imply a central concentration of millions or billions of solar masses in a tiny volume, consistent with supermassive black holes. Some supermassive black holes reveal themselves through their energetic emissions. When a supermassive black hole accretes matter rapidly, the accretion disk becomes so luminous that it can outshine the entire galaxy. These are quasars and active galactic nuclei, among the brightest persistent sources of light in the universe. The fact that such enormous luminosity comes from such a small region, and that this region is at the center of a galaxy, points unmistakably to a supermassive black hole. In 2019, the Event Horizon Telescope collaboration achieved something once thought impossible. They imaged a black hole's shadow. The Event Horizon Telescope isn't a single telescope, but rather a network of radio telescopes spread across the Earth. By combining their signals using a technique called very long baseline interferometry, they created a virtual telescope the size of Earth, capable of resolving features as small as the event horizons of the nearest supermassive black holes. Their first target was the black hole in Messier 87, a giant elliptical galaxy about 55 million light-years away. The image showed a dark shadow, the black hole's event horizon and the region just inside it, surrounded by a bright ring of emission from the accretion disk. The light from the far side of the disk is bent around the black hole by its gravity, creating a bright ring that's asymmetric due to relativistic effects. The image matched theoretical predictions remarkably well and provided direct visual evidence of an event horizon. In 2022, the Event Horizon Telescope released an image of Sagittarius A, our galaxy's central black hole. This was more challenging because Sagittarius AA's is smaller and the gas around it is turbulent, changing on timescales of minutes. The image again showed a dark shadow surrounded by a bright ring, confirming the presence of an event horizon. Perhaps the most revolutionary method for detecting black holes is gravitational wave astronomy. Gravitational waves are ripples in spacetime itself, predicted by Einstein's general relativity, but not directly detected until September 2015. When LIGO detected gravitational waves from two merging black holes, it opened a completely new window on the universe. Gravitational waves are emitted by accelerating masses, but they're incredibly weak. Only the most violent events in the universe produce gravitational waves strong enough to detect across cosmic distances. The merger of two black holes is perfect for this. As the black holes spiral together, they emit gravitational waves that carry away energy and angular momentum, causing the orbit to shrink. The waves get stronger and higher in frequency as the orbit tightens, creating a characteristic chirp signal. At the moment of merger, a final burst of gravitational waves is released as the remnant black hole settles into its final state. LIGO and its partners detect gravitational waves by using laser interferometry. Each detector consists of two perpendicular arms, each several kilometers long with mirrors at the ends. A laser beam is split and sent down both arms, reflected back, and recombined. Normally, the beams interfere destructively, canceling out. But when a gravitational wave passes through, it stretches space in one direction while compressing it in the perpendicular direction, changing the arm's lengths by a tiny amount. This changes the interference pattern, creating a detectable signal. The changes in length are astonishingly small. LIGO can detect changes smaller than 1/10,000th the diameter of a proton. This extraordinary sensitivity allows it to detect black hole mergers from billions of light-years away. Since that first detection, LIGO, Virgo, and Kagra have detected hundreds of black hole mergers, building up a census of stellar mass and intermediate mass black holes throughout the universe. Gravitational waves provide unique information. They tell us the masses and spins of the merging black holes. They reveal how common binary black hole systems are and what masses they typically have. They provide tests of general relativity in the strong field regime, where gravity is most extreme. And they've revealed black holes with unexpected properties, like those in the pair instability mass gap, challenging our understanding of stellar evolution and black hole formation. Future gravitational wave detectors will probe even more of the universe. The planned LISA mission, a space-based interferometer, will detect gravitational waves from merging supermassive black holes, offering insights into how these giants form and grow. Ground-based detectors like Cosmic Explorer and Einstein Telescope, proposed for the coming decades, will have even greater sensitivity, allowing them to detect black hole mergers from the early universe and map out black hole populations across cosmic time. Black holes have also been detected indirectly through their effects on light. Gravitational lensing occurs when a massive object bends the path of light passing near it. A black hole can act as a lens, distorting or magnifying the image of objects behind it. In some cases, a black hole might pass in front of a background star, briefly magnifying its light in a characteristic way. Detecting these microlensing events provides another method for finding dark, massive objects, including potentially isolated black holes not in binary systems. As you breathe slowly and feel yourself sinking deeper into relaxation, consider how remarkable it is that we can study objects that are fundamentally invisible. Through X-rays from accretion disks, through the orbital motion of stars, through the ripples in space-time itself, we've learned to see black holes despite their darkness. We've measured their masses, their spins, their numbers, their effects on galaxies. We've even captured images of their shadows. From objects once purely theoretical, existing only in equations, black holes have become observable, measurable features of the universe we inhabit. They're no longer speculative curiosities, but observed phenomena, as real as any star or planet, revealing the cosmos at its most extreme. Conclusion: the universe of black holes. We've journeyed together through the entire spectrum of black holes, from those formed in the death throes of massive stars to those possibly born in the first fraction of a second after the Big Bang itself. We've explored stellar mass black holes scattered throughout galaxies, the silent remnants of stars that once blazed in the night sky. We've visited the supermassive giants anchoring galaxy centers, engines of unimaginable power that shape the evolution of cosmic structures. We've searched for intermediate mass black holes, the elusive missing links that bridge the gap between small and giant. And we've contemplated primordial black holes, hypothetical relics from the universe's beginning. We've seen how black holes can rotate, warping space-time into whirlpools around themselves, creating ergospheres and enabling the extraction of rotational energy. We've explored the physics of accretion disks and jets, the quantum mysteries of Hawking, radiation, and black hole thermodynamics, the information paradoxes that challenge our deepest theories. And we've learned how astronomers detect these invisible objects through their effects on light, on matter, and on space-time itself. Black holes are more than just cosmic curiosities. They're fundamental features of the universe, playing crucial roles in how galaxies form and evolve. They're laboratories where physics reaches its extremes, where general relativity and quantum mechanics collide, where our understanding is tested and sometimes found wanting. They're symbols of the ultimate unknown, regions from which information cannot return, hiding singularities where our current theories break down. Yet they're also accessible to study. Through decades of observations and theoretical work, we've learned an enormous amount about black holes. We know they exist, we know how to find them, and we're learning how they behave. The Event Horizon Telescope has shown us their shadows. LIGO has let us hear them merge. Future observations will reveal even more, showing us black holes across cosmic time, teaching us about the universe's history and evolution. As you drift into sleep now, let yourself feel the vastness of the cosmos and the strange beauty of these objects. In the darkness behind your closed eyes, you might picture the universe as it is, vast beyond measure, filled with hundreds of billions of galaxies, each containing its own black holes. Some are small and isolated, wandering invisibly through the space between stars. Others blaze at galaxy centers, surrounded by brilliant accretion disks, powering jets that stretch across the cosmos. Still others merge in pairs, sending gravitational waves rippling through the fabric of space-time itself. Black holes remind us how much we've learned and how much remains to discover. They're testaments to human curiosity and ingenuity, to our ability to understand the universe through mathematics and observation, to piece together the nature of objects we can never directly see or touch. They're also reminders of mystery, of limits to knowledge, of questions still unanswered and perhaps unanswerable. But most of all, they're simply wondrous. The universe contains objects so strange, so extreme, that they challenge everything we think we know about reality. Regions where time slows and space warps, where gravity becomes so strong that light itself cannot escape, where matter is crushed to infinite density. These are black holes, the darkness within the light, the ultimate mystery, and the ultimate expression of gravity's power. Thank you for joining me on this journey through the universe of black holes. If you found peace or wonder in these cosmic explorations, please consider subscribing to the Science Pillow. Each video is an invitation to discover, to learn, and to find tranquility in the vast tapestry of scientific knowledge. A like helps others find this quiet corner of the cosmos. And if there are other topics you'd like to explore together, other mysteries you'd like to unwind with, let me know in the comments. For now, rest easy. Let the universe's grand mysteries fade into the background as sleep takes over. Know that out there, in the darkness between the stars, black holes are performing their cosmic dance, bending space-time, consuming matter, slowly evaporating through quantum processes, shaping the universe we call home. And know that we, tiny beings on a small planet, have learned to understand them, at least a little, through the power of human curiosity and reason. Sleep well and dream of the cosmos.